Alright, hello everybody, and welcome to the final lecture of Chemistry 103. Today we're going to talk about alkenes, alkynes, and aromatic compounds, which are some of the simplest organic molecules. So, organic molecules are sometimes referred to as hydrocarbons because they contain hydrogen, oxygen, and carbon. And we generally group carbons into various groups. In this case of alkanes, we call them unsaturated hydrocarbons. And this means they do not contain the maximum number of hydrogen atoms that could be attached to each carbon atom. They are referred to as alkenes when they contain carbon-carbon double bonds, and they're referred to as alkynes when they contain carbon-carbon triple bonds. These, in general, will react with hydrogen gas to form saturated hydrocarbons. And in general, alkenes have a bond angle of 120 degrees between the hydrogens and have a trigonal planar structure. And alkynes have a 180 degree bond angle because of the triple bond. Now, alkenes, like we said a moment ago, contain carbon-carbon double bonds. This means that the two adjacent carbon atoms share two pairs of valence electrons. And this forces them into a flat shape because the double bonded atoms lie in the same plane, and this gives them the trigonal planar arrangement around the double bonded carbon atoms. An example of an alkene is ethene. This is the simplest one. It's also known as ethylene. It has the formula C2H4, and it's two carbon atoms connected by a double bond. It is used to accelerate the ripening of fruits, and in fact is given off by fruits to ripen themselves, which is why if you put them in any paper bag, the ethylene gas will build up and cause the fruit to ripen faster. Now, alkynes, they have a carbon-carbon triple bond, meaning that they share three pairs of electrons between the two carbons. This is why it has a 180 degree bond angle, because the other known pair is sticking straight off the other side due to a great amount of repulsion from the three electron pairs between the two carbons. An example of this is ethyne or acetylene. This has the formula C2H2, and the triple bond connecting the carbon atoms can react with oxygen to have a combustion reaction that exists at a very high temperature, above 3,300 degrees Celsius, and therefore it's used in welding and in torches. So, real quick set of examples. Identify each of the following compounds as an alkane, alkene, or alkyne. So A is has a carbon-carbon triple bond, which means that it's an alkyne. B has a carbon-carbon double bond here, which means that it's an alkene. This structure is a reduced structure that shows, it assumes that every atom at each vertex is equal to carbon. And so in this case, you have carbon with a single bond to another carbon with a single bond to a third carbon, and then there's a double bond between the third and fourth carbons, which makes this an alkene. And then this structure here is also all carbon atoms, so you have carbons at each point with the line between them representing a single bond, and each terminal point has the correct number of hydrogens to make up for the rest of the single bonds, which makes this an alkane. So there are naming conventions for these molecules. In general, you name the alkane chain for the longest carbon atom, and then you change the ending if there are double or triple bonds present. So an alkane such as ethane is two CH3 groups with a single bond between them. The same two carbon chain with a double bond is ethene or ethylene, and the same carbon chain with a triple bond is ethyne. And then if you continue on to a three carbon chain, that is propane. If you have the same carbon chain with one double bond, that's propene. And if you have the same 3-carbon chain with one triple bond, that's propyne. So, in general, you name the longest carbon chain that contains the double or triple bond. Then you number the carbon chain from the end nearer the double or triple bond. Then you give the location and name of each substituent in alphabetical order as a prefix to the alkane or alkyne name. So an example of this, writing the IUPAC name for the following molecule, which has CH2 double bonded to CH, bonded to CH2, bonded to CH3. And then B, name this, which has carbon single bonded to carbon, which is triple bonded to carbon, which is single bonded to carbon, which then has these two branching structures here. So step 1 is name the longest carbon chain that contains a double or triple bond. So in the case of A, we have a double bond, and that means it's an alkene. So we will replace ane with ene. And for a triple bond, that means that it's an alkyne, you replace ane with ine. Step 2, we have to name the longest carbon chain that contains a double or triple bond. In the first case, there's only one chain, so it's CH2 here. There's 4 carbons in this chain, which would normally make that butane. However, because of the existence of the double bond, it's butene. And then this one here, if you count the number of carbons, there's 1, 2, 3, 4, 5, 6, 7, which is the longest chain, making this what normally would be heptane, but then it's actually heptyne because there's a triple bond. And then you have to number the carbon chains to indicate where the different substituents are. So in the case of A, you start the numbering at the end closer to the double bond, and that means that the name of this molecule is 1-butene because the double bond occurs at the position of the first carbon. Now, in this case of heptyne, the triple bond occurs between the second and third carbons, so this would be 2-heptyne. And now there's also one more thing to do. In the case of butene, there's no substituents, but for heptyne, there's a methyl group or a CH3 group coming off here, and it's coming off the 4th carbon, and so this molecule would be 4-methyl-2-heptyne. Now there's another type of organic molecule called a cycloalkene. It's like a cycloalkane. It contains a ring structure, and you can either be substituents or no substituents. If you don't have any substituents, the double bond doesn't need a number because it's self-explanatory, but if there's substituents, you have to number the carbons so that you can know where the position of the substituent is relative to the carbon, relative to the double bond. So in the case of cyclopentene, you have 5 carbons making it a cyclopentane, and then you have a double bond making it cyclopentene. And then in this case, you have a 6-carbon ring, which is cyclohexane, but then the addition of the double bond makes it cyclohexene. And then if you start counting from the double bond, you have carbon 1, carbon 2, carbon 3, and then you have a methyl group, so it is a 3-methyl cyclohexene. So the condensed structural formula is the skeleton structure of carbon networks that we showed before that doesn't have any atomic symbols in it. So in the case of 2-hexyne, you want to make a 6-membered carbon chain with a triple bond at the second carbon. And in the case of 3-methyl-3-hexene, you have to make a 6-membered carbon chain with a double bond at the third carbon and also a methyl substituent at the third carbon. So we do that by here we have CH3, single bonded to C with a triple bond at the second carbon, single bonded to CH2, single bonded to CH2, single bonded to CH3, which is the terminal carbon. And then for 3-methyl-3-hexene, you have a 6-membered carbon chain, and then at the third carbon you have a double bond to carbon, and then a methyl substituent. Now, when you have a double bond, you can have a molecule that has two molecules with the same chemical formula but a different chemical structure. So these are called cis and trans isomers. They generally have different physical and chemical properties, and they occur because these double bonds are rigid and cannot rotate. So when you have two substituents that are adjacent to one another on the double bond, we refer to this as cis, and when they are across from one another, as shown here in the bottom, we call it trans. So an example of this is 1,2-dichloroethene. So this is an ethene molecule with two chlorines in the place of two of the hydrogens, and the chlorine atoms can either be on the same side of the double bond, as shown here. This would be called cis 1,2-dichloroethene, or they could be arranged across from one another, as shown on the right, which is referred to as trans 1,2-dichloroethene. And these isomers do not occur if one of the atoms in the double bond has identical groups. So, for instance, if you have two hydrogens, there is no cis-trans isomerization in this 1-butene molecule. And also in this 2-methyl-propene molecule, you have two hydrogens on the one carbon and two methyls on the other carbon, and so it doesn't matter which orientation this is, they're identical to one another. We name these compounds by placing cis or trans in front of the name and numbering the substituents. So in this example, we have cis 1,2-dibromoethene and trans 1,2-dibromoethene. You can also draw these molecules based on their names. So say we have 2-hexene, we can draw the cis and trans isomers of that by drawing the condensed structural formula first. We have CH3, CH with a double bond to another CH, and then we have the 4-carbon chain on this side. So then on one side of the double bond we have hydrogen and a 1-carbon group, and on the other side of the double bond we have a hydrogen and a 3-carbon group. These two different groups are attached to each carbon on the double bond, and therefore they can exist in two configurations. The first one, the cis isomer, occurs when the two hydrogens are pointing up and the two other substituents are pointing down. This is cis 2-hexene. And then the trans isomer occurs when you have the methyl group adjacent and opposite of the propyl group, and this is trans 2-hexene. Now, pheromones are an example of where the cis-trans isomerization of a molecule can become very important. So, pheromones are chemical messengers emitted by insects in tiny quantities. One that's called bombicol is emitted by the silkworm moth to attract other moths and has one cis and one trans double bond. So here we can see this long carbon chain with an OH at the end. It comes here to a carbon-carbon double bond that is trans, and then the next carbon-carbon double bond is cis, because these two substituents are on the same side and these two substituents are opposite sides. So name each of the following compounds, taking into account whether they are cis or trans. So A, you have a carbon-carbon double bond with a bromine on each carbon bond on the same side. For B, you have a carbon-carbon double bond with two methyl groups opposite one another. And for C, you have a carbon-carbon double bond with two chlorines on one carbon and a methyl and hydrogen group on the other carbon. So the first one, A, is cis 1,2-dibromoethene, which we have discussed already. B is trans 2-butene because the two carbon substituents are on opposite sides of the carbon double bond. And then C is 1,1-dichloropropene. There is no cis or trans isomerization because of the two chlorines attached to one of the carbons. Now, these molecules can undergo reactions because of the double bond, and these are called addition reactions because reactants add to the carbon atoms in double or triple bonds and break the double or triple bonds to provide electrons to form new bonds. So in general, if you have an alkene and it reacts with a molecule AB, then A will add to one carbon and B will add to the other carbon. So there are a number of addition reactions that we're going to talk about. There's something called hydrogenation, where you add hydrogen to an alkene or an alkyne to produce an alkane. This is used heavily in the food industry to make saturated fats out of unsaturated fats. There's also something called halogenation, where you add a halogen molecule like chlorine or bromine to alkene or alkynes, and this makes a haloalkene. There's hydrohalogenation, where you add a hydrochloric acid or hydrobromic acid to an alkene to make a haloalkane. And then there's hydration, where you add water, which forms a strong acid and alcohol, or which forms alcohol in the presence of a strong acid. So the first reaction is called hydrogenation. It's where you add hydrogen atoms directly to the carbon atoms of a double or triple bond. Usually requires a catalyst such as platinum, palladium, or nickel to speed up the reaction. And in general, the reaction occurs on the surface of such a metal. So the reaction consists of an alkene and hydrogen gas to form an alkane. Such an example is butene, 2-butene in this case. You have double bond between the second and third carbons, and hydrogen adds to it, breaking the double bond and adding hydrogen to each of the carbon atoms that had the double bond between them to make butane. So this is generally used to hydrogenate oils. Adds H2 to double bonds in vegetable oil to produce compounds with higher melting points, which is useful for homogenization and also in cooking. They are solids at room temperature. Examples of this are margarine and shortening. If we want to hydrogenate 1-butane using a platinum catalyst, how would we do this? So we would set up our equation. We know that 1-butene means that the double bond is between the first and second carbon atoms, and then the rest is this normally singly bonded carbon chain. Hydrogenation involves the addition of hydrogen gas, and we need to use a platinum catalyst, and therefore it breaks the double bond between the first and second carbon, adding hydrogen to each one and making butane. Some more examples. If we hydrogenate each of these alkenes, what is produced? So the first one is 2-butene. The hydrogen will add to the second and third carbon atoms, breaking the double bond to form butane. And this is cyclopropene. If we add a hydrogen molecule to this in the presence of platinum, it will break the double bond between these two carbons and add hydrogen, leaving behind cyclopropane. Halogenation is when you add halogen atoms, such as chlorine or bromine, to the carbon atoms of a double or triple bond. So you have an alkene or an alkane, or an alkene or an alkyne, and then you have X, which refers to the halogen, and each of the atoms from the molecule adds to each of the carbons on the double bond, making a dihaloalkane. These reactions are very rapid and don't generally require a catalyst. And some examples are shown below. If you have ethene and you mix it with bromine molecules, the bromine molecules will add to the double bond and make dibromoethane. And if you have propine and you add 2 chlorine molecules to it, the chlorine molecules will both add to each of the carbon atoms on either side of the triple bond and give you tetrachloropropane. This can be used to test for unsaturation. If you have an oil and you add bromine to it, liquid bromine, if you add it to an alkane, there's nowhere for the bromine to react, and the red color of the bromine will persist. However, if you have alkene or alkyne present, the red color of the bromine will disappear because it will react with the alkene or alkyne to form a haloalkane. So here are a couple of examples. Draw the condensed structural formula of the product of each of the following addition reactions. If you have 2-butene and you add chlorine gas to it, what will happen? And if you have cyclohexene and you add bromine liquid to it, what will happen? So in the first case, the chlorine molecule will add to each of the carbons on either side of the double bond and form dichlorobutane. In the case of the cyclohexene, the bromine will add to either side of the double bond in the ring and make 1,2-dibromocyclohexane. Now, there's also hydrohalogenation, where you add HCl or HBr to the double bond, and this takes the form alkene plus HX yields a hydroalkane with H on one carbon and X on the other. Some examples of this are shown here. You have 2-butene plus HCl yields 2-chlorobutane, and cyclopentene plus HBr yields bromocyclopentane. So hydrohalogenation reactions occur in 2 steps. The first step involves protonation of the double bond, where you add hydrogen to one of the carbons. This steals electron density from the bond and leaves one of the carbons positively charged. Then the bromide ion that's left behind is attracted to this positive charge center and migrates to the positively charged carbocation and forms bromoethane. In general, this can be described by something called Markovnikovs Rule. So in asymmetrical alkenes, the H in the HX adds to the carbon in the double bond that has the greater number of hydrogen atoms. So there's an example shown here of this unsymmetrical butene molecule. One of the carbons has 2 methyl groups attached to it. One of them has 1 and a hydrogen. The hydrogen from HBr will favor attachment to the carbon that has more hydrogens attached to it, because the methyl groups will stabilize the positive charge on the other carbon atom. In general, if you do this reaction, you will encounter only this product and none of this product, because this is energetically unfavored. Now, the last reaction is hydration, where you use a strong acid to force water to add to a double bond. The hydrogen atom bonds to one of the carbons in the double bond, and the OH bonds to the other. This converts an alkene into an alcohol, and happens in the case of 2-butene plus water yields 1-butanol, 2-butanol. Now, hydration occurs with a double bond that has an unequal number of hydrogen atoms. The hydrogen atom bonded to the carbon in the double bond that has more hydrogen atoms will accept the hydrogen, and the OH bond to the carbon that has the fewer number of hydrogen atoms, just like in Markovnikovs Rule. So because we can establish a fairly consistent method for predicting how these addition reactions will occur, we can use them to make things called polymers, which in general are large molecules that consist of small repeating units called monomers. They're found in nature, such as molecules like cellulose in plants, starches in foods, and proteins and DNA in the body. They can also be made synthetically, such as polyethylene and polystyrene, or Teflon or nylon. And they're often made by the reaction of small alkynes at high temperature and pressure. So a polymerization reaction is when you cause these monomers to join together. So ethylene is shown here. If you add them together under high pressure and high heat, the double bonds will break and they will fuse together to form repeating monomer units of this. Now, polyethylene is one of the common synthetic polymers. PVC is another one, polyvinyl chloride. Polypropylene is used in a lot of clothing. Polytetrafluoroethylene is Teflon. Saran wrap is polydichloroethylene. And styrofoam is polystyrene. So you can make polymers from many different alkenes. The simplest one is ethylene or polyethylene. It's used to make plastic bottles, film, insulation materials. Chloroethene, it's also known as vinyl chloride. This can be used to make polyvinyl chloride or PVC, which is used to make plastic pipes and tubing, garden hoses, and garbage bags. Then there's propene or propylene. This can be used to make polypropylene, which is used for ski and hiking clothing, carpets, and artificial joints. Then you can have tetrafluoroethene, which is shown here. This can be made into polytetrafluoroethylene or Teflon, which is used for non-stick coatings. There's 1,1-dichloroethene, which you can use to make polydichloroethene or saran wrap. And then phenylethene or styrene can be made into polystyrene, which is used for plastic coffee cups and cartons or insulation. And all of these have different indications that are usually printed on them, which indicate how they are to be recycled. So polyethylene terephthalate is one that we didn't talk about. That's PETE plastic, which is indicated by a number 1. And then high-density polyethylene, polyvinyl chloride, low-density polyethylene, polypropylene, polystyrene. And then 7 is used to designate other. These can be useful in plastic recycling if you need to maintain the purity of whichever plastic you're working with. Now, one more thing we have to talk about is aromatic compounds, the symbol of which is benzene. We've talked about benzene before in this class. Benzene is a 6-carbon ring that has 6 electrons shared equally among the 6 carbon atoms in the form of 3 delocalized double bonds. These behave very similarly to alkanes because they do not undergo addition reactions because of the stability of this delocalized electron structure. And these are sometimes shown as a hexagon with a circle drawn inside to indicate that it is a single unit. Most aromatic compounds are based on benzene in some way. Many of them have very fragrant odors, and therefore the name comes from that. Examples of this are anise or anisole, which is a benzene ring attached to an oxygen and a methyl group. Another one is tarragon or estragol, which is the same thing except with another carbon substituent on the other side. And then thymol, the scent of thyme, is a benzene ring with these 3 substituents. Now in general, here's some more common ones. TNT is an aromatic compound. It is when you have benzene substituted with nitrate groups or nitro groups. Then you have ibuprofen, which is a somewhat more complicated molecule with a benzene ring at the center. Aspirin has a carboxylic acid group and an ester group attached to it. And then vanillin has a ketone group, an ester group, and a OH group. So we name aromatic compounds by starting with the first. If we have one substituent, we just name it according to whatever substituent is attached to it, and then having benzene in the name. So examples are methylbenzene and chlorobenzene for singly substituted benzene molecules. There are some common names for singly substituted benzene molecules because they were discovered before we understood molecular structure. And so things like methylbenzene is also referred to as toluene, which you may have heard of. Aminobenzene is also known as aniline, and phenol is benzene with an OH or alcohol group. You can also have two groups on a benzene ring. In this case, you number the ring to give the lowest numbers to the side groups, and then use prefixes to show the arrangement of the substituents, as shown below. So if the substituents are on the first and second carbon, it's called the ortho configuration. If they're on the first and third carbon, it's the meta configuration, and if they're on the first and fourth carbon, it's para. We'll do some examples. So if you have methylbenzene with a chlorine on the third carbon from the methyl group, we call this 3-chlorotoluene or metachlorotoluene because it's in the first and third carbons. If you have two chlorines opposite one another on the first and fourth, you have para-dichlorobenzene. And then if you have an OH group and a chlorine group on 1 and 2, you call this 2-chlorophenol or orthochlorophenol. Now, xylene is the common name for all of the isomers of dimethylbenzene, which is benzene with two methyl constituents on it. Since there are 3 different isomers, we have to name them accordingly. So if we have the methyl groups on the 1 and 2 carbons, it's orthoxylene. If we have them on the 1 and 3 carbons, it's metaxylene. And if we're on the first and fourth carbons, it's paraxylene. And all of these have slightly different properties. And there are also situations in which you may have 3 substituents on your benzene ring. Some examples shown here: 1,3,5-trichlorobenzene, 4-bromo-2-chlorotoluene, because the methyl group is the first carbon in this case, and then 2,6-dibromo-4-chlorotoluene for the toluene molecule is carbon 1, and then it has bromine on the second and sixth carbons and chlorine on the fourth. Now, aromatic compounds are grouped together because they have similar properties. They generally have higher melting and boiling points because of how flat and symmetrical the rings are. They are generally not soluble in water. The exception is if they contain OH or C or carboxylic acid substituents, in which case they may be lightly soluble in water. The aromatic bonding system is very stable, and this makes it resistant to reactions that would break them up. However, they are flammable, just like other hydrocarbons, and when burned, release a great deal of energy. This will conclude our discussion of the basics of organic chemistry.